An archer standing on a 30-meter high building shoots an arrow with a velocity of 10 meters per second at an angle of 45 degrees relative to the horizontal. Calculate the magnitude of the horizontal and vertical components of the arrow's initial velocity, how much time it takes for the arrow to reach the ground, and the range of the arrow. So if I draw what this would look like, you would have like the building here, and then the arrows being shot off, and it's going to follow the path of an object in projectile motion. And the building is 30 meters high, and its initial velocity is 10 meters per second. So the first question asks us to calculate the horizontal and vertical components of the initial velocity of this arrow. So let's say that this vector represents the initial velocity, right? Actually, write VO here. And these, let's say, are its horizontal and vertical components. This is the vertical component, VOY, and this is the horizontal component of the initial velocity. Now, if you look at this, you'll notice that the horizontal and vertical components are perpendicular to each other, and that makes a right angle. So this is a right triangle. And if this is our launch angle, theta, here in that case, this is the angle at which you launch it. You can use some trigonometry to say that the initial y velocity is simply the initial velocity times the sine of theta. This is simply because sine theta is the opposite over the hypotenuse. So it's the, if you write this down, is the opposite over the hypotenuse. And then we're just simply solving for the initial y velocity. This is the same here, except this time it is using the cosine since it is the adjacent over the hypotenuse. And so that is how you would solve the first part here. Here is the magnitude. And we know that theta is 45 degrees. So this would be about 7.07 meters per second. You can write it in square root form, but I'm just going to write it like this. Probably should have specified the initial velocity as being 10 meters per second. And then this is, you do the same thing with the y component. And the cosine of 45 degrees is equal to the sine of 45 degrees. And I believe it was square root of 2 over 2. So their values are actually both going to be equal here. And so that is part A. I'll rewrite it. I'm just going to use 7.07 meters per second in my future calculations. Okay, so that's the first part. Now we need to figure out the time it takes for the arrow to reach the ground. So you might remember this kinematic equation that says that the change in x, or the displacement of an object, is equal to the initial velocity of that object times the time interval plus 1/2 times the acceleration times the time interval squared. And we can actually apply this in the y direction as well. And in this case, our initial velocity is simply the initial velocity in the y direction. And our acceleration is simply the gravitational acceleration, or g. And it's negative since it's pointing in the downward direction. So now the change in y is also the height of the building, the negative of the height, since no matter where it goes, the displacement will always be minus 30 meters, since it eventually always just lands somewhere on the ground. So now we can just simply plug everything in and solve for t. So from this we get minus 30, change in y, is equal to the initial velocity in the y direction times the time interval, minus 1/2 times the gravitational acceleration, which is negative 4.9 t squared. So you can just rearrange this. And we've got a quadratic, which we can simply solve using the quadratic equation, which I think is minus 7 minus b plus minus the square root of b squared minus 4ac. Okay, I'm running a little bit out of room, but I think it's all over 2a. Okay, now if you solve this, you should get that your two solutions are t equals about 3.30 seconds. Yeah. And these are not exact, but I just simply rounded it. And t equals minus 1.86 seconds. And out of these two, you need to actually pick which one is correct. And in this case, it would be the first one of 3.3 seconds, since you can't have a negative time interval. So this one here is simply just not possible. There is no negative time interval. So we can ignore this one. So we have figured out the time that it was in the air from that equation. So for B, the time that was in the air is about 3.3 seconds. 3 seconds. And now all we need to do is calculate the range of the arrow. And this last part is quite easy. So the range, we can simply use this kinematic equation again. The change in x is equal to the initial velocity times the time interval plus 1/2 times acceleration times time squared. And in this case, the change in x, or the displacement in the x direction, is simply going to be the range. It's just this range here. It doesn't matter how far up it goes in the air. It's just this here. And then the range is equal to the initial velocity in the x direction times the time. And we don't have to worry about acceleration, since the acceleration in the x direction is simply 0. There's no propeller or rocket attached to it that's making it go further. So there's no acceleration, so we can omit this whole part of the equation. So now we just need to plug everything in. Figure out that the initial x velocity is 7.07 meters per second. And the time interval is 3.3 seconds. So solving this, you should get that the range is equal to about 23.3 meters. Again, I rounded this to 3 significant figures. And that is how you would solve this problem here.